I'm Alex from Anodot, and if you don't know, for some reason, what we are doing, we are building an autonomous business monitoring solution and anomaly detection on a large scale. So how large? This is an actual screenshot from our monitor, system monitor, and yes, we are using Anodot to monitor ourselves, like eating our own dog food. And you can see 500 million metrics in our system, and it's much more in terms of data points, since even like a 1 minute roll-up metric will send at least 1,000 data points daily, so like do your math. We have millions of anomalies in our system, and we are reducing this number by 2 orders of magnitude using correlation, and this is exactly the process we are going to review today. We work with some of the biggest companies in the market, and most of them you know. And as additional requirement, we need to support both on-prem and SaaS customers. So correlation at scale is a complex subject, and to understand it better, we will break it down into the building blocks. So what's our agenda for today? I will explain you how our system works. We'll present you some algorithms we are using and discuss some internals. We will look at correlation methods we are using and calculations used for online and offline phase. And today, most of the time, we will spend on LSH because it's our secret ingredient for scale. And also, we will review our system architecture and talk about the data flow in our system. So how the system works. We do it in 5 steps. We collect customer metrics from different channels, like database connections, API calls, and analyze like every metric in real time. For this reason, the baseline is created, reflecting our understanding on how the metric should behave, and any inconsistency between the actual behavior and our baseline is the anomaly. So once the anomaly is detected, we want to correlate it with all the similar anomalies, ongoing anomalies in the system, and send the alert to the customer. At the end of the process, customer can give us a feedback about the alert quality. So here you can see how we monitor a single metric. The blue line is the number of active customers in the system, and the shaded area is the baseline we are creating automatically for every metric in the system. In the first few points, the baseline is wide. Then Anodot learns the daily pattern, okay, and the baseline becomes tire. After a few weeks of time, you can see the Anodot detected actually weekly seasonality, and the baseline becomes very small, like almost invisible, perfectly matching the metric. Okay. In the second example, you can see the deviation from the norm, which is discovered as anomaly in the system. Why do we need a correlation mechanism at all? Okay, I will discuss those points briefly and show you some supporting examples on the next slide. So first of all, it helps us in root cause analysis. Okay, if multiple metrics are related, we want to discover the reason for this relationship. Okay, but actually the reason is the interesting part, right? And the second one, we don't want to send all the alerts, like alert per anomaly we are finding, because it can be like tens of thousands of daily alerts. It's like full-time job just to check all those. Instead, we want just to send just a few meaningful anomaly groups to the customer. Okay, this is the example supporting root cause analysis. So we found 2 separate anomalies in the system, like spike in API errors and the same time drop in payments metric. Okay, we discovered the anomalies are actually correlated somehow and part of the same anomaly group. So I want to analyze the anomaly group and say API is not working, which is why payments drop. Okay, so we are not analyzing a single anomaly, but a large incident in the system using the anomaly group. And this is the second example from current Anodot customer based on 1 day of data. Okay, running almost 4 million metrics in the system, we can discover thousands of daily anomalies. And we're correlating everything into much smaller number of anomaly groups and sending just tens of meaningful alerts about the data. Okay. Before using Anodot, the same customer worked with 50,000 daily alerts, which is insane. Okay, at this point, you understand we must have some correlation mechanism, but how do we correlate? Okay, we have at least 3 primary algorithms in our system. I will drill down into each one of those and try to explain pros and cons. The first one and most straightforward type of correlation is graph correlation. The customer can explicitly provide it using regex expression. Okay. Or we can implicitly figure it out using relevant system configuration as alert configuration, for example. Also, multiple metrics created from the same data source are related. You can think about it as multiple group bytes from the same table, for example. So any anomaly in the data will affect each of the group bytes separately, but you understand the same anomaly in the data, right? So we can correlate all the alerts together, all the anomalies together. What is good about this method? Regex is a relatively simple calculation, and there is no need for a model, okay? No offline process here. But you can smell a challenge, and you know, if you have a problem and want to solve it with regex, now we have 2 problems. And this is exactly the way it works in production. Name correlation is calculated using a distance between metric names. Okay, the logic is a metric with almost identical or closely related names can be correlated. Okay, probably are similar. Again, you can think about I don't know, shoe sales and umbrella sales for London for a specific period of time. As you can see in the example, the algorithm is TF-IDF-ish, and we will give a penalty for overused tokens in the system, right? Unlike in this toy example, the real metric can have tens of tokens in the metric name, and total dictionary size can be tens of thousands of tokens. Hence, dimensionality reduction is applied here to have a fixed output vector size from this model. Okay, the good part about this approach is it's metadata based. Okay, we don't need to analyze actual metric data to use it, and it's easy to explain to the customer, but only if you have a meaningful and consistent metric names in the system, which is also not always the case. Okay, abnormal correlation is the third and even more exciting type of correlation. It's based on actual metric behavior, okay, and common anomalies across metrics. Okay, if metrics fail the same way during the same period of time, like all the time, those metrics should be related somehow. Okay, we just need to find the relationship. So the next time both are triggered, we will create a joint abnormality group. Again, we need some punishment for large anomalies in the system. Okay, if you have anomaly in like 80% of the metrics in the system for a specific customer, probably it's not a good anomaly for abnormal correlation. Okay, the good part about it, it captures the actual metric behavior. Okay, but its limited science needs historical data. Okay, so it can be used for cold start. Actually, in our system, we are using it for cold start, but using simulation. So we are running simulation on historical data and then using the abnormal, like even for new customer. So 2 important requirements we have here. We can't keep the model in the memory, like all the vectors for all the metrics we have. And we can't calculate the correlation between all the abnormal metrics to all the abnormal metrics in real time. You can think about it like this way. We need to compare any new anomaly with all the opened anomalies in the system. Okay, so it's not for online. Okay, we understand we can fulfill those requirements during online phase, so we'll need some offline process. Okay, we'll discuss the offline. How can we do it? LSH is actually here to help us. You remember, it's our secret ingredient for scale. And we will spend the next few minutes discussing it, the algorithm itself, and how we're using it. So instead of calculating actual vector similarity, we can use LSH approximation to keep a tiny model of potential candidates with very high recall. Okay, so we calculate hash codes, aka signatures, for each metric and in the system and use it during the online phase. Let me take into the details of the process. Okay, so assuming this is your vector space you are working with, first of all, we are randomizing hyperplanes and checking the vector position relatively to the hyperplane, like 1 or 0 side for each vector. Okay, so again, like the black points are vectors and the lines are hyperplanes. Okay, so the red bucket signature is 1, 0, 1. Okay, because it's on the one side of H1, 0 side of H2, and 1 side of H3. And you can see sort of color buckets generated by this process. So once we need to find a good candidate for any of the red vectors, we will check only our red vectors. Okay, vectors having the same LSH signature. Okay, one more trick we are doing here, we are converting actually the binary representation to decimal and creating sort of bucket ID, right? So 101 is decimal 5, so the red bucket ID is 5. One benefit of LSH, it has just 2 optimization parameters: the number of hyperplanes you are using in each model and the number of randomized LSH models. Okay, so let's discuss those, like each one of those parameters. How can we find the optimal number of hyperparameters per model? To give you some intuition about the number of hyperplanes, let's think about like extreme cases. So extreme case number 1, single hyperplane per model. Okay, it will give you a huge average bucket size. If you are unlikely, you can have like all your vectors in the same bucket. And you understand the trade-off here. It will be very expensive to use this model, but it's very cheap to calculate it, right? The second extreme case is actually a lot of hyperplanes, right, per model. In this case, you have like 0 to 1 vectors per bucket, and it's completely useless, right? Because you can't find any good candidates here. Like the best you can find is the vector itself in the bucket. Okay, and you want your bucket size somewhere in the middle. And the system design actually will be affected by number of compares you want to run during the online phase. Okay, bigger bucket size, smaller model, more to compare. And the opposite. Now let's think about the second hyperparameter. The second hyperparameter, how can we find the optimal number of LSH models to randomize? And why do you need to randomize more than one model at all? Okay, so the number of models you are randomizing will directly affect the total system recall, since you have non-zero chance of putting almost identical vectors into separate buckets. Okay, we are not measuring like any distances here, all the process random, right? So the more models you will randomize, higher the overall recall of the system. Okay, in this example, we use 3 different LSH models to generate the signature for each vector in exactly the same vector space. Okay, but in each vector will have a different bucket ID in each model. Okay, all the combined bucket numbers is the LSH signature we are using. Okay, for this specific vector. For example, you see the diamond vector from the beginning. It has signature of 520, and the funny part here, it's actually the only vector having this signature. Again, like toy example, right? No, nothing solid, just funny. Okay, let's talk about LSH complexity little. Assuming n vectors and d dimensions and k hyperplanes you have, dk will be the number of operations to assign the bucket to the vector. Okay, because it's like dimensions by hyperplanes. And L is the number of models we are randomizing. So LSH complexity will be about log n, which is like cool. Assuming k about log n as well, which is also like a valid assumption. Science, like you can think about like log of 100 millions is 8. and it's the number of hyperplanes you're going to use, so it's fine. Just want to show you LSH usage is much cheaper than regular index, so obviously brute force calculation. Again, we are comparing like log n to square root n or n. Do you want to take a picture? Okay, next time. Now we need now we want to understand how. Now we understand how we created the LSH model, but how we're going to use it. Okay. So each signature is a vector of L digit. Each digit is a bucket number of LSH model you are randomizing. Okay. In our example, we randomized 3 different LSH models, so we have a signature of 3 digits for each vector in our system. Okay. This way, the bag of signatures represents your vector space, and we have some query vector we want to compare with. So in our case, the query vector is 520. And we are starting from choosing the candidates with the same bucket number in at least one model. Okay, so we are finding any vectors having signature, having 5 as first digit, 2 as second digit, or 0 as third digit. Okay. Now we found those, and we want to compare the actual distance. Okay, we are working with cosine similarity, and we want to compare actual cosine similarity between the candidates and the query vector. And this is the next step. So we are measuring the distance and dropping all the vectors below the threshold. Okay. So in this toy example, you can see we found like 4 vectors from the bag of signatures, and keeping just 2 vectors with the cosine similarity above threshold. You can take it as a 100% recall with 50% precision. Again, in a real system, it's fine to work with single, like 5% precision, 10% precision is fine. How does the offline data pipeline work? We are doing it in 5 steps again. We are processing the data, raw data samples from our customers to extract metric names and anomalies for abnormal correlation, and create the vectors and LSH model and the results. Then, after we are storing LSH signatures, so we are storing LSH signatures and the vectors for online usage, and the storage in our case is Cassandra cluster in online. Okay. And now, so what's going on online phase? You can think about it. We are finding any anomaly. We are comparing, like finding the candidates using LSH signatures, comparing the actual vectors to the query vector or to the anomaly we found, and then creating a new anomaly group or adding the anomaly into any existing anomaly group in the system. Okay, calling it like correlation graph. A few optimizations we are doing during the online phase. So first of all, we are not checking all the correlations model in the system, only the first matching one. We are stopping checking after the first model. If you remember, we have graph, name, and abnormal correlation. Only one will survive at the end. For the same reason, we are checking most promising model first. Okay, it can be most promising, like statistically promising, or just the cheapest one. Okay, so for example, graph correlation is very cheap, so we can first check graph correlation just in case we can find it. Also, we are loading the data on demand only. We don't want to keep all the vectors in the memory all the time, right? Only the cached vectors. And to reduce the number of calculations, we will always compare the smaller graph to the bigger one. You can think about merge of large correlation groups. So we have multiple graphs here. We will take the smaller graph and compare it to the larger. Okay. So now you have all the building blocks, and this is what the complete architecture looks like. The process starts from the customer data ingested by Anodot system in different left side, you can see offline model generation process, and the data is located in the data lake, and the Hive Spark process running to generate vectors and LSH signatures. On the right side, you can see the online process, which is actually correlation graph, and the grouper. Okay. In the middle is the real-time anomaly detection process, which sends each anomaly to the stream grouper consumes. Okay. The grouper will load the model, LSH model, will compare the vector distances and add the anomaly into the correlation graph. Again, it can be existing or new correlation group. During the last year, we made a few improvements to this setup. The major one was partial replacement of Hive process with Spark. Our issue with Hive is the slow processing for compressed data. So the data preparation actually took more time than the actual data processing, like calculations, okay? Especially it's very sensitive to like a lot of small files. If you have in a system, it can be like significantly degrade the performance. After replacing, we can save the same amount of data at about 10% of the previous storage, and the total flow execution time is much faster due to faster I/O. Okay, we can load the data much faster for processing. Okay, if there is one thing I want to take from correlation scale is a complex challenge, and we discussed how to overcome it with algorithms to help you handling big data. And we wrapped it by reviewing and understanding our architecture and discussed potential improvements you can do. So next time you encounter building architecture for big data, make sure to check LSH algorithm and be able to customize it for your needs. I think, yeah. Please ping me with any questions. I promised at least to ping you back.